In this chapter, we're going to spend most of our time looking at conversion between carboxylic acids and other acid derivatives through nucleophilic acyl substitution. And we're also going to look at the interconversion of different acid derivatives as well through the same nucleophilic acyl substitution reaction. But we're also going to quickly look at reductions of carboxylic acids, deprotonation of a carboxylic acid with base, and then in the next chapter, we're going to look at alpha substitution of not only carboxylic acids, but acid derivatives as well. You might recall that alcohols will react with thionyl chloride to make an alkyl chloride. So this is a reaction we saw earlier this semester. We can also convert the hydroxyl group of a carboxylic acid with thionyl chloride into an acid chloride. Here's a second example with this benzoic acid derivative. If we add thionyl chloride, we can convert it into an acid chloride. Here's another example with acetic acid. If we add thionyl chloride, it will be converted into this acid chloride product here. Now the mechanism starts off with the oxygen of the hydroxyl group pushing electrons towards the carbonyl, and then the oxygen of the carbonyl will attack the sulfur, eliminate the chlorine, and form a bond between the oxygen and sulfur. We have this protonated carbonyl now on this side of the molecule. So base such as water or the chloride that got eliminated can remove this hydrogen, get rid of the positive charge, give us now what's called a chlorosulfite intermediate. This chlorosulfite, note that essentially what we have done is we have replaced the OH group of the carboxylic acid into a better leaving group, which is this chlorosulfite. The chlorine from the thionyl chloride that was eliminated in the first step can now add to this carbon, break the double bond. Then the tetrahedral intermediate can reform the carbonyl by eliminating this leaving group. Note that this step is an acyl substitution. So addition of a nucleophile to the carbonyl, and then the tetrahedral intermediate will lead to breaking down, forming the carbonyl, eliminating the leaving group, and as a result, we end up with the acid chloride. Now, in the first step of this mechanism, we saw that it was the oxygen of the carbonyl that actually attacked as a nucleophile this thionyl chloride, the electrophile. We're going to see this several times this chapter. So in general, between the two oxygens on a carboxylic acid or any acid derivative like an ester, the carbonyl oxygen is usually more nucleophilic than this oxygen here. And one way of thinking about this is if we push electrons, the lone pair on this oxygen towards the carbonyl, we have this other resonance form that has a negative charge on this oxygen. So in general, the oxygen of the carbonyl is more nucleophilic than the other oxygen on this carboxylic acid. Earlier this semester, we talked about a reaction that converts alcohols into alkyl bromides. We can use for this transformation a reagent called phosphorus tribromide. Very similarly, we can convert a carboxylic acid into an acid bromide by using phosphorus tribromide. Benzoic acid can also be converted into benzoyl bromide by using phosphorus tribromide. Here's one more example with acetic acid. If we add PBr3, it will be converted into acetyl bromide. The mechanism is pretty similar to what we saw with thionyl chloride. So it starts off with the lone pair on this OH oxygen, pushing electrons towards the carbonyl. The carbonyl oxygen then attacks the electrophile, which is this phosphorus, and eliminates one of the halogens on the phosphorus. That gets us to this intermediate. Base removes a proton to give us the key intermediate in this mechanism is called a dibromophosphite. Notice that we have turned the OH group into a intermediate that has a good leaving group. And now Br negative, which is the bromine that was eliminated in the first step, can add to the carbonyl carbon, break the double bond. We get to a tetrahedral intermediate, which then reforms the carbonyl, eliminates the leaving group to give us this acid bromide. Notice that the last two steps is an acyl substitution, where bromine is the nucleophile and adds to this acid derivative and replaces the leaving group. Carboxylic acids can be converted into esters a number of ways. One of those is by reaction with an alkyl halide. You might recall a reaction earlier this semester called the Williamson ether synthesis, which involves starting with an alcohol, adding base, such as sodium hydroxide or sodium hydride, followed by an alkylating agent like methyl bromide. The base removes the proton on the alcohol, and then the oxygen is more nucleophilic and therefore attacks this electrophile, eliminating the bromine. As a result, we get an SN2 reaction and we end up with an ether. We have essentially replaced the hydrogen on the alcohol with a methyl group. We could do a similar reaction with carboxylic acids that replaces the hydrogen on the carboxylic acid with an alkyl group. So adding sodium hydroxide or sodium hydride followed by an alkylating agent will lead us to an ester. The base removes the proton on the carboxylic acid to give us a conjugate base. This is now more nucleophilic than the carboxylic acid, so this oxygen can now attack a carbon that has a leaving group to do an SN2 reaction, and we end up with an ester. Since this is an SN2 reaction, just like the Williamson ether synthesis, it's best to use unhindered alkyl halides. So primary alkyl halides are best for this, or even methyl halides. In the cases of acetate nucleophiles, they are not very basic, so you can also do SN2 reactions with secondary alkyl halides pretty well. Here's another example with benzoic acid. If we add base, you will get the conjugate base of this carboxylic acid, which is more nucleophilic. And so this oxygen will now add to this secondary carbon and do an SN2 reaction. Now, since it is an SN2 reaction, we're going to get a inversion of stereochemistry in the product, which we see here. Classic reaction in organic chemistry is the Fischer esterification reaction. This is a reaction where a carboxylic acid, such as benzoic acid, reacts with an alcohol. In this example, we're using ethanol. The reaction is typically done under acidic conditions with an acid catalyst such as HCl. And the reaction leads to an ester product, in this case ethyl benzoate, and then a water molecule as a byproduct. Now this reaction is reversible, and so anytime we have an ester and we add water and an acid catalyst, we can usually reverse the reaction and go back to the carboxylic acid and the alcohol. Since this is a reversible reaction, we can use Le Chatelier's principle to shift the equilibrium one way or the other. For example, using an excess of alcohol or carboxylic acid will push the reaction towards product. removing one of the products, for example, removing the water through distillation or some sort of drying agent that soaks up the water, will also push the reaction towards product. As mentioned before, we can push the reaction towards the carboxylic acid by adding water in excess or adding, and generally this wouldn't be practical, but you could, I guess, theoretically add an excess of the ester as well to push the reaction towards the reactant. You could also remove an alcohol from the reaction through distillation. So again, that would push the reaction towards the left side of this reaction. Here's another example with this propanoic acid and isopropanol. If we use ACl as a catalyst, we can make an ester, which is shown here, plus a water molecule. Here's the mechanism for the Fischer esterification reaction. It starts off with a carboxylic acid being protonated by ACl or other acid catalysts. Then water will add to the carbonyl of the carboxylic acid, breaking the double bond, leading to this intermediate, which then loses a proton. So although not shown here, another water molecule can come along and pick up this hydrogen. So that would occur as follows. So either water or some other base in the reaction can pick up this proton, break that bond, give those electrons to the oxygen, get rid of the positive charge on the oxygen, and that leads us to this tetrahedral intermediate. In the next step, water will remove this proton, form a carbonyl by eliminating the leaving group. Now notice the OH is now protonated, so that's a step that actually occurs before the elimination. So a hydronium ion can do this in the previous step. So this oxygen can pick up a proton from the hydronium ion, and that hydronium ion can form from ACl reacting with water, for example. You have now a better leaving group here, and so when the water removes this proton, we can easily eliminate that hydroxyl group that is protonated. That essentially leads us to the final product, which is the ester. So overall, we have replaced a hydroxyl group with an alkoxide group by this acid catalyzed acyl substitution. There's a third method that is used to make esters from carboxylic acids. That involves using a reagent called dicyclohexylcarbodiamide, which is abbreviated as DCC. So this is an alternative to the Fischer esterification. It avoids having to use an excess of alcohol or carboxylic acid, which we usually use in the Fischer esterification to push the reaction towards products. With DCC, we can use one equivalent of an alcohol, one equivalent of a carboxylic acid, and DCC will join them together into an ester. And then there will be a byproduct called DCU, which stands for dicyclohexylurea. This is the structure of DCC. You don't need to memorize it. It's what we call a carbodiamide. Essentially, is two imine groups attached to the same carbon. Here's another example of this reaction with benzoic acid and ethanol. DCC will join them to make ethyl benzoate plus a byproduct of DCU. Here's another example of this DCC promoted reaction involving acetic acid and methanol to make methyl acetate. And then there's also a DCU byproduct. The mechanism for this reaction is as follows. So the DCC has a couple of nitrogens which can act as bases. One of those nitrogens will pick up a proton from acetic acid and form the conjugate base, which is the acetate ion. That also gives you a DCC molecule that's protonated. This acetate ion is now more nucleophilic. This carbon is now more electrophilic. So the acetate ion attacks the carbon, breaks this double bond. They're joined together now. And then in the next step, we're going to do an acyl substitution where the alcohol adds to the carbonyl, breaks the double bond. We get a tetrahedral intermediate. And then that tetrahedral intermediate breaks down to reform the carbonyl and eliminate the leaving group, as shown here. As a result, we get the ester, and we get this DCU byproduct. In this question, we want to try to attempt to prepare the following ester with a corresponding carboxylic acid. So in this question, we want to make the following ester from a carboxylic acid. In this chapter, we looked at 3 different reactions that can do this. So one of them was the Fischer esterification. The other one was with DCC. And then the first one we looked at was taking a carboxylic acid, adding base and an alkyl group through an alkylation reaction. We can pretty much use any of the 3 reactions in this example, since the reaction or the question is not very specific. For example, we could use the Fischer esterification. If we look at our ester and imagine breaking it here, the left side would be carboxylic acid, the right side would be an alcohol, so methanol from the right side, and then butanoic acid from the left side. So butanoic acid plus methanol plus ACl through a Fischer esterification will lead us to that ester. It will be a water molecule as a byproduct. Alternatively, we can use DCC for the same reaction. So we could use the same 2 reactants plus DCC, and it'll make that ester. And a third reaction would involve, instead of using methanol, we would use an alkyl halide, for example, methyl bromide. We would also use a base. So for example, sodium hydroxide. So that would be step 1. And then step 2 would be this methyl bromide, and we could get to that same ester. Carboxylic acids can be converted into amides, sometimes simply by heating a carboxylic acid with the appropriate amine. For example, ethylamine, as shown here, can be mixed with propanoic acid, heated to be converted into this amide. A water byproduct will also result. Now, the reason why this reaction is relatively slow and the reason we need to heat it is because when you mix an amine, which is basic, and a carboxylic acid, which is acidic, the first thing that's going to happen is the nitrogen will deprotonate the carboxylic acid, and you get these 2 byproducts, an acetate ion and an ammonium ion. If we heat these 2, then we can get the nitrogen to attack the carbonyl and replace the hydroxyl group on it, and you get a substitution reaction. Now the problem with this step is, or this route is, that our electrophile is negatively charged and our nucleophile has a positive charge. So this is the reverse of what we want typically for a substitution reaction to occur. So for that reason, we have to heat this reaction, and sometimes to quite high temperatures. Now, a much easier way, and usually the way that we try to do this conversion, is by taking a carboxylic acid and an amine, and instead of heating it, using DCC. DCC will convert an amine and a carboxylic acid into an amide. And then there will be a byproduct of DCU. Note that this reaction we saw earlier, a similar example with esters. So we could use an alcohol and a carboxylic acid to make esters with DCC. This reaction has traditionally been used to make peptides. So amino acids can be joined with DCC. You might recall that amino acids have a carboxylic acid and an amino group on the same carbon. And then they also often have some sort of side group that differs depending on the amino acid. By joining two amino acids, by reacting a carboxylic acid from one and an amino group from the other, we can make an amide bond as shown here, and as a result we get a dipeptide. Now we can repeat this process multiple times and grow this chain and make a fairly large peptide. In fact, this reaction is so simple that automation has been added to it. There are certain instruments that are used to make large peptides by taking different amino acids in a sequence that you uh, input into the instrument. The instrument will mix different amino acids in the appropriate sequence, adding DCC each step, and then washing the peptide that results, and then adding the next amino acid that needs to be added on the peptide plus DCC to repeat the process and grow a chain in an automatic way. Here is a look at the mechanism for the DCC promoted reaction between carboxylic acids and amines. It starts off with the DCC, the nitrogen on the DCC, deprotonating a carboxylic acid, giving you the conjugate base, which is now more nucleophilic and able to attack this carbon of the protonated DCC, breaking the double bond here. Now they're joined together in the next intermediate. The amine will add to the carbonyl carbon through an acyl substitution, break this bond here. And then in the next step, which we see here, we can reform that carbonyl by eliminating the leaving group and therefore forming DCU plus the amide. Anhydrides traditionally are made by heating two molecules of a carboxylic acid to make a symmetrical anhydride. Now, this reaction has been used for many years to make industrially acid anhydrides. Now, this reaction, for the most part, is not practical for most acid anhydrides, so there are better ways to make them, at least on a smaller scale in a lab. Also, note that this reaction, where we heat two molecules of a carboxylic acid, always produces a symmetrical anhydride. So if you wanted an unsymmetrical anhydride, you have to use a different method. So an alternative method to make anhydrides is from an acid chloride. So if we take a carboxylic acid and we add base, we will deprotonate this hydrogen, make that oxygen more nucleophilic. That oxygen can now attack an acid chloride, do an acyl substitution, and eliminate this chlorine. And so now the oxygen will be bonded to the carbonyl, and you therefore form a anhydride as a result. Now this example I'm showing leads to a symmetrical anhydride, but if we use a different acid chloride with a different alkyl group than the carboxylic acid here, you don't necessarily have to form a symmetrical anhydride. Here's another example of making an anhydride from a carboxylic acid and an acid chloride. So if we add base, we will remove the acidic proton on the carboxylic acid. That leads us to this conjugate base, which is more nucleophilic since it has a negative charge on the oxygen. That oxygen can attack an acid anhydride. break the double bond, give us a tetrahedral intermediate. The tetrahedral intermediate will reform the carbonyl by eliminating the leaving group, which is the chlorine, and that gives us the anhydride. Now notice this anhydride is unsymmetrical since the alkyl groups on the carboxylic acid is different from the acid anhydride. As we saw earlier this semester, carboxylic acids can be converted into alcohols by a reduction reaction with lithium aluminum hydride. We start off with this carboxylic acid, we add lithium aluminum hydride, followed by aqueous acid. We can convert it into a primary alcohol. The reaction starts by the hydride on lithium aluminum hydride, adding to the carbon of the carbonyl here, breaking the double bond, then reforming the carbonyl and eliminating the OH group to give you an aldehyde. Now this intermediate is not really isolated. Aldehydes, as we know, can also react with lithium aluminum hydride, and so another equivalent of lithium aluminum hydride will add to this aldehyde carbon to give you an alkoxide ion. This won't react any further until we add aqueous acid, so the oxygen will be protonated by the acid and give you a primary alcohol. Note that other hydride reagents such as sodium borohydride or Dibol are not able to do this type of reaction.